There is a number whose digits can never be fully known, not because our computers lack power, but because the laws of logic strictly forbid it. And it's not the only one. Mathematics is filled with numbers. Most are ordinary, some are useful, but a few seem to appear so persistently across nature, geometry, physics, and computation that they begin to feel less like human inventions, but more like cosmic discoveries waiting inside reality itself. These constants emerge where we least expect them. Inside spirals and black holes, inside prime numbers and randomness, inside growth, decay, turbulence, and information itself. Some describe harmony, others describe chaos. A few appear to mark the very limits of human knowledge. Today, we explore 7 mathematical constants that are not merely important but strangely profound. Every circle in the universe secretly contains the same number. No matter its size, no matter where it exists, the ratio between a circle's circumference and its diameter is eternally fixed. It is an infinite, non-repeating decimal hiding inside every wheel, orbit, ripple, and sphere. Pi first emerged from simple ancient geometry, but over centuries, mathematicians watched in astonishment as it appeared in places where circles had vanished completely. In the quantum probability of subatomic particles, the ripples of fluid dynamics, the mechanics of sound engineering, and the gravitational warping of relativity. It is as if curved space-time itself cannot exist without pi quietly embedded inside its fabric. A ratio discovered in ancient circles turned out to be woven into quantum physics itself. But if pi governs the geometry of curves, what governs the mathematics of change? If pi governs curves, then E governs change. This strange number emerges whenever growth continuously feeds upon itself. Population booms, radioactive decay, compound interest, heat flow, wave equations, and quantum states. Again and again, nature seems to prefer the mathematics of the exponential function. Euler's number possesses a remarkable, almost magical property. The function f of x equals exponential of x is its own derivative. Its rate of change is perfectly equal to its current value. That deceptively simple relationship makes E the natural language of any process that evolves continuously through time. And then comes what is widely considered the most beautiful equation ever written. The golden ratio has fascinated artists, architects, philosophers, and mathematicians for centuries. Its defining geometric property feels beautifully recursive. Its defining property feels almost magical. The whole relates to the larger part exactly as the larger part relates to the smaller. This recursive balance creates structures that appear aesthetically satisfying to many people. The golden ratio does appear in certain biological growth patterns and spiral structures, particularly where efficient packing or recursive growth is involved. Though popular culture has often exaggerated how universal it truly is, still its mathematical behavior remains extraordinary. It appears in pentagons, continued fractions, the Fibonacci sequence, and dynamical systems. Even more strangely, powers of V remains deeply connected to the Fibonacci numbers through elegant identities that almost seem designed rather than discovered. Whether or not nature truly prefers the golden ratio, humanity has spent centuries projecting ideas of beauty, balance, and harmony onto it. And perhaps that says something profound about us as well. Some constants describe perfect order, but Euler-Mascheroni constant gamma describes a tiny failure of order that never disappears. Imagine laying a jagged staircase made of unit fractions over a perfectly smooth curve. As the staircase stretches out toward infinity, you might expect a mismatch between the two to eventually average out, to smooth itself away. It doesn't. It locks tightly into a single permanent value. The value is gamma. More precisely, it is defined as the limiting difference between the harmonic series and natural logarithm. It emerges from the mysterious borderland between two worlds, the discrete world of counting individual numbers and the continuous world of smooth curves. If pi measures roundness, gamma measures a sort of mathematical friction, the persistent misalignment between the pixelated and the smooth. And unlike pi or e, humanity is still remarkably blind to its true nature. We have calculated trillions of digits of gamma, yet we still don't know if it is rational or irrational. It quietly sits on a knife edge of modern number theory, resisting classification. If gamma describes the friction between order and flow, what happens when a system is pushed so far that order collapses entirely? Chaos often looks completely random, but sometimes hidden deep underneath apparent disorder. Mathematics reveals an astonishing blueprint. In the 1970s, physicist Michel Feigenbaum discovered that completely different chaotic systems shared the exact same numerical behavior. Dripping faucets, population dynamics, fluid turbulence, and electrical circuits. Systems with absolutely nothing in common all approached chaos at the exact same rhythm. Again and again, a single number appeared. As a steady system is pushed toward instability, its state splits into a cycle of 2, then 4, then 8, a process called bifurcation. The Feigenbaum constant measures the universal rate of acceleration for this countdown to absolute chaos. The terrifying part was this: chaos was not truly chaotic. Chaos is not pure randomness after all. It has a rigid architecture, a universal grammar. Unrelated chaotic systems are all secretly following the exact same script on their way into the dark. But chaos, at least, can be described. What about a number that actively resists description? A number that spent centuries defying the world's greatest mathematical minds. Some numbers become famous because they explain everything. Others become famous because they stubbornly refuse to be explained. Apéry's constant is the value of the Riemann zeta function at integer 3. At first glance, it looks entirely harmless, just another neat, infinite series of cubed numbers. Yet, for centuries, the world's greatest minds could not determine if this number was even irrational. Then, in 1978, a relatively obscure French mathematician named Roger Apéry stunned the global mathematical community. He proved that zeta 3 was irrational, using a bizarre, highly unexpected technique that few people initially believed could work. The shock was not merely that the proof succeeded, but that it exposed how little we actually understand about these higher power series. Even today, Apéry's constant remains shrouded in mystery. Mathematicians still cannot prove whether it is transcendental. A simple-looking infinite sum continues to quietly defy our most sophisticated tools. If Apéry's constant resists our understanding, what lies at the very boundary of what mathematics can ever know? There exists a number whose digits can never be fully known, not because our computers lack power, but because the laws of logic strictly forbid it. This is Chaitin's constant, omega. Imagine writing a computer program completely at random, just typing random instructions and hitting run. What is the probability that it eventually stops rather than looping forever? Omega is exactly that probability. Simple enough so far, but here is where things get strange. The digits of omega are completely random, not just in practice, but in principle. There is no pattern, no shortcut, no formula that can predict the next digit. Each one stands entirely alone. To decode even a single additional digit, you would need to solve Alan Turing's famous halting problem, determining whether any given program stops or runs forever. Turing himself proved that no general solution exists. To fully decode omega, you would need to solve it infinitely many times. The cruel irony is that buried inside those unknowable digits are answers to some of the deepest unsolved questions in mathematics, truths that conventional proof may never reach. For centuries, mathematics was seen as the one domain where every truth could eventually be found. Omega shattered that belief. There are things that are true but can never be proven true. Omega is not just a strange number. It is proof that mathematics has a hard outer boundary, a wall that human logic can approach but never cross. These 7 constants are far more than tools for calculation. They are the recurring fingerprints left across reality itself. We began with the most familiar, a number hiding inside every circle, every ripple, every orbit. We ended at the edge of what logic itself can reach, a number whose digits sit permanently beyond the reach of proof itself. In between, we found the language of growth, the architecture of packing, the friction between the discrete and the continuous, the grammar of chaos, the silence of a number that spent centuries refusing to be understood, and finally, the place where human certainty simply ends. Again and again, as we peel back the layers of our universe, mathematics uncovers the same unsettling, beautiful possibility. The universe may not merely obey mathematics. It may, at some fundamental level, be mathematical. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.